I'm gonna switch to English. I hope that you don't mind because it would be a bit weird to give this talk in Portuguese. I forgot many technical words, so it's like, I don't know. Okay, so the idea is I would like to talk to you about some works I've done in this direction, connecting gravitational particle production and leptogenesis. So let me just start with the main issue that we want to solve, is the existence of this baryon asymmetry in the universe. We know that there is more matter than antimatter in the universe, and there are many ways to look at this. We can parameterize this asymmetry via this so-called baryon to photon ratio, which has been measured by looking at the CMB, at the power spectrum of the CMB, and also by looking at BBN. So we know by looking experimentally about this. If you want to have, let's say, the generation of a baryon asymmetry starting from a universe which had no asymmetry, so let's say that you start with a universe without any difference between matter and antimatter, and you want to generate it dynamically, you need to fulfill the so-called Sakharov conditions. First, you want a surplus of baryons over the ones you already have, baryons or leptons. Besides, you need some CP violations because you want to bias the production of matter over antimatter. And also, you need to be away from thermal equilibrium because in thermal equilibrium, any ray that produces matter would equally produce antimatter because of thermal equilibrium. So these are the three general conditions that all baryogenesis models, meaning all models that want to produce this number, have to fulfill. One of the most interesting, and the one I'm going to focus from now on, is the so-called leptogenesis. In this case, you include to the standard model right-handed neutrinos, and with some Majorana masses and some Yukawa couplings with the lepton doublets. And in this case, this is very interesting because first, the idea of introducing these right-handed neutrinos is to understand the smallness of neutrino masses. Because when you look at this Mn, since this is like not protected by the symmetries of the standard model of particles, this can have any number. And when you look at the diagonalization of these two terms, you find that the masses of the active neutrinos is inversely proportional to this mass, assuming this mass much larger than the electroweak vacuum expectation. So in this way, you are explaining why, for instance, the neutrino masses are in a different scale, like they are very, very small comparison to the charged leptons or charged fermions. Because you have this ratio between the VF square over this Majorana mass. And this should be afforded, let's say, 0.1. But people notice that, oh, if you already have these terms, you will fulfill all Sakharov conditions. First, because you have lepton number violation, because these are Majorana neutrinos, and by that, you won't have any conservation of any number. Second, because you have new sources, new possible sources of CP violation in these Yukawa parameters that you include here. And third, since these right-handed neutrinos can be very massive, they can be produced in the early universe, and you can have situations in which you have deviation for thermal equilibrium. I will explain this in a bit more detail.
Can you explain this first graph on the right?
This one?
Yeah, the right one.
Oh, sorry, yes.
Yeah, what is this?
This is the measurement of the different densities of the primordial elements. So you have the different combinations of the elements, and what is your measurement related to the CMB. So this is basically the abundances. Yeah, no. Well, this is the abundances of the quantities of these elements in the early universe that you can infer as function of the baryon of photon ratio. And I think these are the measurements, the bands are the measurements. And then you compare with the CMB measurement here. There is actually a problem that you can see here. All these are compatible. Let's say they have this coincidence with the CMV value, but the lithium prefers a smaller value of the baryon to lepton, baryon to photons. Okay. Any question? Okay, but as I was mentioning, the right-handed neutrinos can have any mass in principle because they are not protected by the electroweak symmetries. So in principle, you can have different types of leptogenesis depending on the actual masses of the right-handed neutrinos. On one hand, you can have what is called high-scale leptogenesis, in which these right-handed neutrinos are very heavy, or 10 to the 12 GeV. And in that case, you don't need Yukawas to be small, but you have, for instance, Yukawa of order 1. This is interesting because this can have some connections to some grand unified theories, and that's what people have considered. The problem of this is that we don't have any collider, and probably we won't have any collider to test these very heavy right-handed neutrinos. So this is difficult to test, but it might be connected to the existence of GATs. So if you find some GAT, maybe it can tell you, oh yeah, maybe this is related to this right-handed neutrino. We can go down in the scale. Let's say, for instance, 10 to the 6 GeV. In that case, Yukawas, in order to fulfill the neutrino masses, need to become smaller. And you start to need to add some ingredients. For instance, in some specific models, you need to add some small violation B minus L in order to produce enough baryon asymmetry. It's not, let's say, this is not what I was talking before. You need to add something because it's not enough. You can go down even more. Let's say to 1 TeV. And in this case, Yukawas needs to be very small. And in order to produce enough baryon asymmetry, you start to require some resonant behavior by imposing this type. Let's say you need two right-handed neutrinos, and they need to be very degenerate. And finally, you can go even lower to the 1 GeV scale. And in this case, even though Yukawas are smaller, and you also need this fine-tuning between the splitting of the mass of two right-handed neutrinos, the nice thing is that this could be testable, right? You can have a collider or a beam damp experiment, and when you're looking for these right-handed neutrinos or heavy neutral leptons, as some people call it. So in principle, this works because the process of production of the lepton asymmetry is a bit more complicated, but in principle it works. But it's testable. So this is why this is nice, and people have focused on looking at this. So let me just go back higher to the scale, to the high scale leptogenesis, and talk you a bit more in detail how this works. This is what is called thermal leptogenesis. And let's assume that the universe had a temperature big enough that processes like a lepton with a Higgs interact, producing right-handed neutrinos. And if you assume that there is no initial abundance of these right-handed neutrinos, then you start to create some population of these N via these interactions in the thermal plasma. This start to grow. But at some point, they start to decay. And the decay bias, for instance, the production of leptons over anti-leptons. Because there is some CP violation, we find that when you compute the decay into leptons and anti-leptons, there is a bias, and then you start producing more leptons than anti-leptons because of the decays. Yeah, well, this is the Yukawa term I was talking before, right?
Oh, okay.
This is the usual Yukawa terms. Yeah. Maybe it's not clear, but these are the Yukawa terms. Yeah. Well, this is introduced in the CP violation, which is introduced in Yukawas. So, yeah, well, yes, you need to. Yeah, exactly. Yeah. So we have many freedom in these phases that the Yukawas can have. So in principle, that's why. No. Yeah. Yeah, it's similar to the CP phase in the CK matrix, right? It's there, and we are trying to measure. If we can generate it dynamically, it would be nice, but. No, but in this case, it's the same, right? In this case, you also need to have some phases. So these Yukawa need to be complex, right? Mm-hmm. Yeah. So because of this, the bias decay into leptons and anti-leptons on lepton asymmetry is created. And then, because of some non-perturbative processes, this part of this lepton asymmetry is converted into baryon asymmetry via what's called S-Fallow. Okay? So you can see here the plot is showing you the three different ranges. First, there is the creation of this population of right-handed neutrinos. When the temperature of the universe starts to be of the same order of the mass of the right-handed neutrinos, the production sort of stops, and the abundance of these right-handed neutrinos becomes more or less what you expect in equilibrium. But after that, because the universe is expanding faster than the interactions that are producing the right-handed neutrinos occur, these start just to decay, and basically you start to produce your final baryon asymmetry here, which is the red line. Okay? So you may be asking, what is this? The thing is, when you start, you are depleting leptons over anti-leptons. So you're producing, let's say, a negative lepton asymmetry. But at some point, this is the absolute value, you're crossing zero. right? And your crossing zero is that at the moment in which the abundance of the right-handed neutrinos is equal to the equilibrium abundance, which is related to the third Sakharov condition I was talking to you before, because you have thermal equilibrium. But after that, the decay becomes out of equilibrium, and then you freeze out your baryon symmetry. Right? But let's say this is the simple mechanism, but when we start to look at the details, we need to be careful, and there are some problems that start to appear. So as I was mentioning, the CP violation comes, in this case, from the interference of these three diagrams. And when you look at this, the CP violation phase is related to what is called delta L equal to processes, which are basically processes in which are this. Let's say you convert an anti-lepton to a lepton, or basically you erase two leptons and you only produce Higgs in your plasma. So this type of processes are related to what's called this delta L equal to. But if the universe, if the universe was so hot, there is a point at which these interactions could be in thermal equilibrium. And the problem is, if these interactions start to be in equilibrium, they start to erase the asymmetry that you're producing from the decay of the right-handed neutrinos. This is what is called washout. So the same processes that are producing the right-handed neutrino abundance or the baryon asymmetry, they are also erasing part of what you're creating because of these interactions. So this is the same plot I was showing you before, probably with the different colors. Now the abundance of the right-handed neutrino is this purple, and this dashed blue line is what you expect without including these washout processes. The problem is when you include them for some values here, for instance, this depends on the masses of the active neutrinos and the masses of the right-handed neutrinos. You find that this erase basically all the asymmetry that you're producing. So this is a problem for this so-called high-scale leptogenesis. If the masses of the active neutrinos are in this ballpark, this process will erase the asymmetry, and this is a big problem. So let's say that an experiment that is looking for active neutrinos, the active neutrino mass, for instance, looking at beta decays or so on, you find that you have the neutrino masses are in this energy scale. This high-scale leptogenesis would be in a big tension, because we wouldn't be able to explain the asymmetry that we observe in this scenario. This can be better shown in this plot, which what I'm showing you is the mass of the heaviest neutrino, the active neutrino, as function, well, the right-handed neutrino mass, M1, as function of the heaviest neutrino mass. So we have in the neutrinos have three masses, and we are just selecting the heaviest neutrino mass here. So the dashed line and above would be the parameters that would produce the asymmetry that we observe, varying of the maximizing over the Yukawa parameters. And above this, you could have any asymmetry you want. But this is without this delta L equal to process. Once you include these processes, basically, it's only this gray region that would be available for you to produce the observed asymmetry. So you see, this is cutting a lot of parameter space in this area. The thing is, Catherine and this experiment in Germany is exploring actually these masses here. So if we find the neutrino masses are here, we will be in a big problem in this case. Is there a way to save this scenario? Yes, in principle, it would be nice to produce right-handed neutrinos after these processes are not longer important in the universe. So after this delta L equal to process have pros and cons, and this is what I will comment. Now moving on to the low scale leptogenesis, in which you have right-handed neutrinos. Yes. Yeah.
In this graph, the gray band.
Yeah.
So the parameter space that I have to look for is inside gray, because the gray is the area where this delta L affects. So sorry, outside the gray.
Outside the gray, yes. So the gray is the one that.
Outside the gray.
No, the other way around. Yeah. Oh, the only thing that works is inside the gray region.
So I need a neutrino to be up to maximum 0.1.
Yes. And this right-handed neutrino mass, so a bit heavier. Yeah. Okay. Any other question? No? Okay. Okay, now moving on to the scale of very low leptogenesis, low scale leptogenesis. In this case, I was mentioning before, the nice thing is like you have, let's say, order GV, 110 or 100 GV. And depending on the mixing between these, let's say, right-handed neutrinos with the flavor states, you could look for this in different colliders or in beam dam experiments. So this is why it's nice, because you can test this. The problem is that when you start to look at the parameter space available, and then you look at this washout process I was talking to you before, there is some region that we can test, but if we find right-handed neutrinos here, again, washout processes would be strong, that they would erase the asymmetry that you produce. So in principle, everything that is above this, let's say, blue line in the case of two heavy neutral leptons, or two right-handed neutrinos, would be in trouble because of washout processes. And the only parameter space that you have here is this. So in principle, you would require not finding anything here and expecting some, I don't know, in the FCC or other types of experiments like Dune or CHIP. Okay. Of course, the situation changes if you add the third heavy neutral lepton, because the line is here, but okay, we don't know. Okay. So this is another scenario we will consider later. Oh, sorry. Okay. Before moving on, I will do a bit of shameless self-propaganda. So we have done this code called Ulysses that basically considers all these scenarios of leptogenesis, and they basically it computes what is the value of the baryon asymmetry that you're producing. This is basically including all possible scenarios. So, but no, not all possible. It's not that good, the code, but include many things like the standard cosmology, some spectator effects, loop effects, washout, flavor effects. It's based on solving Boltzmann equations. And the nice thing is, like, let's say if you have a model for leptogenesis, you don't need to like write down the Yukawa parameterization that you want. So everything is there. So if you're interested in it, just let me know. But yeah, this is the propaganda I wanted to do. We are going to have the third version soon, hopefully. Okay, so coming back to our scales of the right-handed neutrino masses, there is an important assumption that I was considering here. The big assumption is that the universe reheated to a temperature big enough to create the right-handed neutrinos. So underlying of everything that I was talking before is that the universe was hot enough to create right-handed neutrinos. If it wasn't, you might be asking what happens in that case, right? So let me just do some diagrammatic way to understand this. Again, the universe should have maybe, did the universe reheat to a higher temperature such that it was bigger than the mass of the right-handed neutrinos? Maybe yes, and in this case, you have thermal leptogenesis. But you need to be careful about washout, because you have either in high-scale leptogenesis, you have this delta L2 equal to processes, or you have upper bound in your mixing, as I was talking before. So maybe a way to solve this is producing right-handed neutrinos after washout processes have frozen out. The second option is no, the universe didn't reheat to a temperature big enough to produce right-handed neutrinos in the plasma. So you need some sort of non-thermal sources to produce your right-handed neutrinos that will produce your baryon asymmetry. In this case, we can think in minimal beyond the standard model scenarios, and maybe in this case, and this is what I'm going to focus from now on, is gravity playing a role. I will consider two types of generation of right-handed neutrinos using gravity, which is a cosmological production and a black hole production. Okay? So we want to understand this interplay here. Okay, so I will just consider what are the generalities of this gravitational particle production. And if this is the only thing you get from my talk, I would be satisfied. This is the most important, okay? Basically, how to create particles from the vacuum. So to understand this, let's consider a simple quantum mechanical analogy. And this is the way to understand this. Let's say that I have, I don't know, some system that is described by this harmonic oscillator, and we prepare it in such a way that is on the ground state. Then by some, let's say we change our experiment somehow in such a way that there is and this is a ground state, right? So we are preparing our system to be in the ground state. If there is some sudden change of this potential, let's say we change our thing, and we don't let the system to have enough time to evolve, what we find here is that with respect to this new potential, what we had as a ground state, it would be no longer a ground state. Okay, and this is because we have a non-adiabatic evolution. We need this sudden change between the two potentials. This is what's saying that you switch something or you do something to your potential, that you change it very fast. A sudden change. Yeah. From the point of the perspective of quantum field theory, it indicates that even if you have some vacuum state, so no particles, with respect to this new potential, you will have some excited state that in quantum field theory is that you will have particles that are created. Okay. So this is important, this having this non-adiabatic evolution in order to produce these particles. What happens, let's say, more in a gravitational wave? Let's say we have some initially stationary universe, like our universe Minkowski, and then we prepare our fields in such a way that the vacuum expectation value of the number operator is 0. So there are no particles, only the vacuum. But then, because of some non-trivial time evolution, we have something that changes our space-time. I will come back what happens there. And then in the future, we have also some stationary universe, some stationary space-time. And then when we look at our prepared state, let's say our what was no particles, we will have the production of particles here. So we will have that particles have been produced here. Okay, and this is like the clue of this production of particles. There are two ways to actually produce this. First, in a cosmological setup, in which you initially had inflation, but then inflation ends and your universe is radiation dominated. So because this change between inflation, your universe deaccelerates and then only evolves through radiation domination, because these two changes of these two different universes, you will produce particles. The second way is what is called black hole gravitational particle. So initially you have some sort of star, and this star, let's say, was Minkowski, but because of collapse, you produce a horizon, and then you also have a different stationary universe after that. And because of this, you will have two different universes, and then you will have some particle production. Okay? So, yes, well, this is the Hawking evaporation, right? So it's not that it emerged from the black hole, it's tricky, but it's related to Hawking evaporation, yeah.
So this process is basically Hawking.
Yes, yes, it's Hawking evaporation. The usual production from inflation, yes. Yeah. Well, sort of, because reheating people usually consider the decay of the inflaton, right? More like normal decay of inflaton, and the decay products thermalize. Yeah. But this is more like from vacuum to vacuum. Okay, any other question? Because I think this is the key part of the talk. So if you.
The only thing is that, I mean, this is a black hole, so it's a thermal part.
Mm-hmm. Yes. Well, it depends on the mass of the black hole, right? And we will see what are the parameter space you need, and that's a question that it's still open in our center. Okay, it's not astrophysical black holes. It will be a different type of black holes. Okay, so people have considered these two scenarios in order to produce dark matter, because in principle, in this case, in the black hole case, you can produce black holes that are heavy enough that they are still around, and they could be part of the dark matter, or they could produce the dark matter via Hawking evaporation. And in this case, because of in this scenario, in the cosmological production, you can have the production of very heavy particles, and these particles don't need to interact with the standard model, and they could be dark matter. The problem is testing these scenarios, but yeah, this is still a possibility. Okay, well, the first part, the cosmological gravitational production, and this is based on this paper. So I will be a bit more technical from now on. So that's what I was saying. That if you got only that part, is that really it's really what matters. But from now on, I need, for instance, to specify what is my inflationary potential and understand the evolution of the different modes of a particle that is created. So we just assume some inflationary potential, so is such that near the origin is some sort of exponential. So sorry, not exponential, phi to the kappas, and some parameters are chosen to be compatible with the observables in the CM. But this is probably more interesting, is understanding this co-moving Hubble radius. And the co-moving Hubble radius is basically telling you what is the radius of the things that are casually connected, okay? So during inflation, this reduces, but after that, it grows. And the growth depends on how the universe is reheated. And it can have different equation of states depending on this parameter kappa here. But at some point, reheating ends, and the universe becomes radiation dominated. And this is what we observe, for instance, during BBN. Okay. So this is more or less to understand what's the different time evolution of the universe parameterized in this co-moving Hubble radius. But okay, so how do we implement this gravitational particle production more in detail? So, sorry, something I forgot to mention. Here, this curly phi or var phi in LaTeX, right? It's the inflaton, but we are going to add now some additional scalar field phi, which doesn't need to be related to inflation. Actually, it needs to be an expectator. So it should be there, but it will be seen, it will see the evolution of the universe. So when we look at the equation of motion of this scalar, we can just do some transformations when this M effective depends on the mass of the scalar and the coupling with gravity, with the rich scalar here. And when we do a transformation, let's say we go to the Fourier space, we obtain this equation of motion for the different modes. I think this is more clear, right? Because this is telling you, oh, when you have this type of equation, what you find is that each mode obeys a harmonic oscillator-like equation, but with a time-dependent frequency. And this is related to the example I was talking to you. If you have some very non-trivial dependence of the theta evolution, you will have the particle productions, because in this case, you're changing the frequency, right? There is a time dependence on the frequency that the oscillator has. So in that case, you will produce particles. Yes, it's the same. Yes, yes. No, then it's the same. The inflaton, the thing is like this is assumed that it doesn't dominate the universe. But because we assume that the inflaton is decaying and it will produce the thermal plasma of the universe. This doesn't need to decay. It doesn't need to be connected to the standard. Or it could be, right? It's, yeah, it could be there. Yeah, yeah. Oh, well, yeah, but this is for a scalar. For instance, you can have other particles. It's not only for a scalar, right? It could be fermions, vectors. I'm just taking the scalar as an example. Okay. So again, you find that these modes, each one obeyed this equation with the time-dependent frequency, and this is the key of the production of particles. Importantly, because of this time dependence, the basis in which basically, let's say, you will parameterize your quantum fields would be different at different times, because they depend on this conformal time eta here. So, and then you need to relate your basis at early times, here called in, with the basis at late times, called here out, via this so-called Bogoliubov coefficients. Okay. Why is this important? Well, you can parameterize your scale, use field chi here and do some transformation. This is not very important. The important thing is like this beta will be related to this Bogoliubov coefficient, and this depends on what is called adiabaticity factor. And this is related to the fact I was telling you before. If the evolution needs to be non-adiabatic in order to produce particles, and this will be parameterized via this factor here. So it depends on how fast, this is why this the derivative of your frequency is changing as function of time, okay? If the change is slow enough, you won't produce enough particles, or if it's fast, you will produce particles, okay? And then if you want to compute the co-moving number density of particles that you created, you need this beta related to this Bogoliubov coefficient, which is just obtained by solving this evolution equation here, this equation of motion. So yeah, this is a bit more technical of how this is computed, okay? But maybe it's more interesting. Well, this is the fermion case. It works more or less the same. The physics is the same, just there are some sign changes here. And the diabaticity factor is a bit different. But let's look more at the plots because probably it's easier to understand. So here I'm just showing you in the bottom plane is this diabaticity factor. It goes from 0, grows, and it goes again to 0. This is from 0 because at some point this factor the derivative is 0, and then because of the change between the inflationary universe to a radiation-dominated universe, there is a non-trivial time dependence, and this adiabaticity factor grows. And this depends on the mode, on the k of the mode, right? So different values I'm putting here, and you see here, this is the production of particles, right? This is the beta parameter, right? So you have, when this is become maximal is when you start to produce particles. Okay, and for green, it happens at different points, and for this orange, produce at different points. So these are different modes on your Fourier transform. This is why this happens at different times. Okay, it's because the universe, it depends on the heating of the universe. Because at some point, the universe is sort of oscillating. Right, it's when the inflaton is oscillating, so the universe also has this behavior. So these are the wiggles where they are being there. Well, I guess what really matters is the asymptotic thing, right? Right. We know that this happens, but what matters is the value asymptotic. So how exactly? Yeah. How much particles are you creating?
You also need the mass to be compared with the curvature.
Yes.
So in other scenarios, you can have particles like transition from radiation to matter.
Yeah. Yes, and this is what I was going to show you now. Because you can compute what is the co-moving number density, the amount of particles that are produced, normalized tensor value, as function of the mass of the particle, here a fermion, related to the Hubble scale at the end of inflation. So this is the relation, more or less, what it's telling you with respect to the curve. So in the fermion case, you see that the largest amount of particle is very, very peaked close when the mass is of the same order of the Hubble parameter at the end of inflation. And choosing, for instance, a value of 10 to the 12 GeV, we find that the largest amount of particles is produced when this happens, when the mass is close to this scale. It depends on the potential of your inflaton, but it's not very much dependent, as you can see here. The lines are different, but the behavior is more or less. So here is where it appears the idea, right? Because I was choosing this number explicitly because of this, right? Because I want to produce heavy right-handed neutrinos via this mechanism, and the largest production happens when the Hubble at the end of inflation is related to this parameter He, okay? This vanishes when the mass goes to 0 because you have conformal symmetry, and when you have conformal symmetry, this doesn't happen, okay? So an important thing is like if you had an universe that was first had a period of inflation, inflation ended, then the universe reheated, and then you had radiation domination, you will produce particles this way. It's unavoidable. It's because of gravity. So this is something that needs to happen, okay? So this is unavoidable, and this is a way to produce particles. So, okay. So the idea is, okay, let's say that the particle that we are interested in producing is the heavy right-handed neutrino that will be afterwards decaying, producing the lepton asymptotic. We need to assume something. We need to assume first that the time scales are different in the sense that the production of the right-handed neutrinos ends before the decay of the particle. The reason of this assumption is a bit more technical. Well, we were not able to include both things at the same time. Like the mode growing and decaying, everything was becoming too complicated to handle numerically and so on. So in principle, this is an assumption. We are assuming that the production of the particles, for instance, the heavy right-handed neutrinos, happens first, and there is some time afterwards they start to decay, producing the baryon asymmetry. Okay? So in principle, we will have that these right-handed neutrinos that are produced from this process, this cosmological production, are produced this way, and then we need to ask ourselves, is this production enough to generate the observed baryon asymmetry? course, if let's say we have this production, we can use this number that we get as initial condition and then evolve these two equations that's telling you, well, if you produce a right-handed neutrino, this will decay producing the lepton asymmetry, and this is basically the lepton asymmetry that's produced. So you are decaying the particles, and then they are producing the B minus L asymmetry or the baryon asymmetry. Okay, these two equations, and this is the solution. Simple. You can do it analytically, and it will depend on the amount of initial, the initial abundance of these right-handed neutrinos that are producing from this CGPP. Okay, these are related here, and it depends on when you stop. Let's say when you stop the production of your valence.
Time dependence. So you put some constraints
Mhm.
to say, well, this had to happen this
Yeah.
set of time.
Yes. Yes, because so I was saying putting the two things like the production, the gravitational production, and the decay, it was complicated. We didn't manage to solve it. Yeah, yeah. We are saying, oh, the gravitational production is fast, let's say, and or the lifetime of the right-handed neutrino is long enough for this to occur first. Okay. Any other question? No. Okay. So we can just look at the different evolution of this, and in this point, it's very important. There is the dependence on this kappa parameter, which was related to the inflaton potential, is actually very important. The reason is that the amount of the right-handed neutrinos that is produced depends on time, and time depends on how the universe is expanding. Okay, because we have the relation between time and the equation of state parameter omega, well, W here, that is related to your inflaton. And also it depends if the right-handed neutrinos are still decaying or not. So in this case, for instance, in the blue line, which is related to kappa equals 6, you see that this parameter, that is basically the abundance of the B minus L asymmetry or the baryon asymmetry, related to the photon asymmetry is growing because these two things are redshifting differently. Because let's say these are being produced, but this is only redshifted. But in this case, both redshifts, let's say the redshift is winning, and this is what is going down. At some point, because of all right-handed neutrinos are mostly decayed, you only have redshift, and this goes down because these are redshifting in a different way, right? You don't have the production of this B minus L, and at the end of reheating, this basically becomes a constant. So there is a non-trivial time dependence on this kappa parameter here. Okay? And we find that kappa needs to have, let's say, if for kappa smaller than this value, you need a large value of your initial abundance in order to produce enough baryon asymmetry to be consistent on what we observe. Okay, so it depends on how the universe actually. Okay, we can just parameterize this for different values of kappa from, let's say, 8, 10, 20. Two main parameters is what is the reheating temperature of the universe as a function of the mass M1 here. Okay. The full lines are the lines that we obtain using the full Bogoliubov coefficient, right? And as you can see here, they peak when Hubble, when the mass is close to the Hubble. So basically, the shape of these lines is related to the number density I was showing you before that peaked when the mass of the particle was of the mass of the fermion was of the same order of the Hubble at the end of inflation. And the dotted lines I'm comparing with some previous paper in which you can do basically the same, but from a different point of view, in which you basically have a, let's say, a scattering of two inflatons mediated by graviton producing the right-handed neutrinos. So this is a perturbative approach that is computed more or less the same, in the way that the inflaton is producing right-handed neutrinos, and these right-handed neutrinos will decay producing the baryons. So you can compare our non-perturbative approach, because we are solving the full equations of motion, with this perturbative approach here. So the perturbative approach is basically our estimating at some values. Oh, yeah. Yeah. No. Yeah, this is. Yeah. Yeah, I don't know if someone has computed via the tunneling model, actually. I'm not sure, not aware. Yeah, I know that the people usually take these two approaches, the perturbative approach and the Bogoliubov approach. But I haven't seen if someone has done the thermal, the tunneling process. So in principle, for some values, our results are closer to this perturbative approach, as you can expect. But when you have big difference with your non-perturbative, between perturbative and non-perturbative approach, because this is overestimating the amount of right-handed neutrinos that you're producing. Okay, because this is perturbative approach overestimates the dashed lines. So the colors are different values of your potential, right? It's like your, yeah. So recall our potential close to the minimum. Let me just, it's proportional to phi to the kappa. Okay. So for different values of kappa, this always overestimates. Actually. Yeah. Okay. Yeah. Before I move on, any other question? Because I'm going to switch gears a lot. Okay. Now I'm going to consider primordial black holes. Okay. So I was talking before about one type of production that is related to the expansion of the universe, the change between an inflationary universe to a radiation-dominated universe. But there is another way to produce right-handed neutrinos via gravity, let's say, which is via Hawking evaporation. In this case, the thing is like, if we want to have lighter black holes that we have measured, let's say we don't want solar mass black holes, but let's say 10 to the something grams, we would need different mechanisms to produce these black holes. And in order to produce lighter black holes, you will need larger densities, like for instance, those that occur in the early universe. So this is what are called primordial black holes. This is a necessary condition, but not sufficient. Sorry, I forgot. But you need to add some ingredients in order to really produce black holes in the early. So you can have different models like bubble collisions, you can have some pressure reduction, or you can have collapse of density fluctuations produced from inflation. A simple way is like, let's say you have some perturbation here, and this perturbation is above some horizon, it will collapse, producing a black hole. This can be parameterized into using two parameters. The initial mass of the black hole to the mass, let's say the things that are in the causal contact with these regions, so the mass content in the horizon, that you're producing. From now on, I will not focus, let's say, not consider a specific model to produce primordial black holes, but only will assume that there is a function of black holes that are parameterized by these two parameters, the initial mass and the initial abundance of these black holes. And also, I will assume that that all black holes are produced with the same mass for simplicity. Okay, we are working on extending this to non-monochromatic distribution. So once these black holes are produced, they start evaporating because of quantum effects, and this is the quantum effects I was talking about. This is related to the what Hawking found when it started to look at the evolution of a collapsing body. The spectrum of this, let's say, or any particle that is produced is sort of thermal in the sense that is proportional, let's say, to either a Bose-Einstein or a Fermi-Dirac distribution. And it depends on the black hole temperature. Let's say, no, we parameterize the temperature of the black hole related to the mass of the black hole in this way. You can, let's say, think of this like a black hole with a mass of 10 to the 13 gram has a temperature of about 1 GeV, okay? But this is not a completely, let's say, Planckian spectrum. And this is because there are some things called gray body factors that deviate it from being a completely Fermi-Dirac or Bose-Einstein distribution. No, this is only related to the fact that when the particle is produced, the curved spacetime behaves like an effective potential. And this effective potential, when you try to cross it, you can have some backscattering, right? So you just look at that this is an effective potential, and the effective potential depends on these different L modes, which are the different wiggles here. and depends on the spin of the particle, because the potential of the particle depends on the spin of it, right? This is what you see, the wiggles, and you only produce modes with such that your L mode is larger than the spin of the particle, and this is why, for instance, the emission of graviton here is like suppressed for low values of this. Okay? And this is a key part of this, because in principle, if you ignore this gray body factor of particles that you produce a lot, if, for instance, you're producing vectors or spin to particles here, so you can see here. Okay, I will skip this because I don't have time. What I was going to mention there is that there are some assumptions that we need to include because of, let's say, they related to the information problem and so on. But what I'm going to assume from now on is like the time evolution of a black hole is parameterized by this equation. And this is simply obtained by looking at every emission of a particle from a black hole will basically decrease a bit its mass. And when you look at the details, you find that the evolution of the m dt is proportional to the 1/m squared mass of the black hole, okay? So this has this very, let's say, weird shape that if this is big, the evolution of this is small. So the black hole is not losing much mass initially. So as you can see here, the change is not very large. But because of this dependence of 1/m squared of the mass of the black hole, when the mass starts to become very small, this comes very fast. So you have this period of what is called an explosion. So the evolution of the mass goes to zero very rapidly in this case. So you see here, this is low then, and then you have this very sharp drop of the masses. Importantly, we will evolve till when the mass of the black hole is close to the, let's say, 100 Planck masses, because below the approximations that Hawking used to derive this spectrum of particles break down. Okay, so we cannot go, let's say, to the Planck scale now. We need to stop before. And this was related to the intermezzo I was going to talk about. Importantly, of course, the mass of the black hole or the lifetime of the black hole depends on particles that can be emitted. Because if you have more particles, it will, let's say, evaporate much faster. And this parameterized via this evaporation function here, which is basically counting all degrees of freedom that can be emitted. And the crucial part is that it depends on all the degrees of freedom that exist. Not only the standard model degrees of freedom, but also all the other things that may exist that may not interact with the standard model. You can imagine sectors or whatever that do not interact with the standard model. But here they will be produced. And as an example from this paper, we are just showing what happens in the simple case if you have massless neutrinos, Majorana neutrinos, and Dirac neutrinos. In the Dirac case, because you can produce the right-handed neutrinos, you produce a bit more neutrinos, so this function is a bit larger because of this. And the difference between massless and the other two cases is that the neutrino mass matters, because at some point the temperature of the black hole would be small, and then you will have a Boltzmann suppression of producing active neutrinos. So this is what happens here. Okay. Of course, there are many limits on the existence of primordial black holes, because depending if these black holes evaporated, for instance, during BBN or the CMB, you would change all the picture, let's say all the standard picture that we have. And for that, we have a strong constraint here. Also, it depends if the black holes have evaporated or not, because if they haven't evaporated, they could be still around, and they could be part of the dark matter. And importantly, there is still some window in which all the dark matter can be made of black holes. And this is what is called the asteroid window, let's say between 10 to the 18 to 10 to the 21 grams. Or we have still this window in which all the dark matter could be made of black holes. Okay? For bigger black holes, you can have other types of limits, like microlensing, like looking very lensing at microscopic scales, gravitational wave, accretion. And for lighter black holes, since they become hotter, you can have productions of the evaporations that we don't observe in satellites. Let's say, I don't know, gamma rays or positrons and so on. And then you have constraints here. Okay? For lighter black holes, let's say below 10 to the 9 gram, which is the region that we're going to focus, this would have evaporated before BBN. So in principle, there are no strong limits in this region of parameters. Why is this interesting? I find this quite interesting because it's a production of particles that is different from what we are used to. In principle, you can produce all particles that exist. So you can produce only gravitationally interacting dark matter or modify freezing freeze-out scenarios. Besides that, you can have modifications on the baryon asymmetry that you have your, let's say, your scenarios. And you can have the production of dark radiation of very boosted particles in which you will mess with delta and effective. And then you can put some constraints. I will focus on the leptogenesis scenario because this is the one that we are considering, right? Yeah.
So I understood that those black holes will stop from, so they could produce whatever.
Anything, everything. Actually, everything.
It will be the same, then it doesn't matter if it's a remedial
No.
or scalable.
Yeah. The thing is, the only suppression you have is the Boltzmann suppression, right? If the mass of the particle is larger than the temperature of the black hole, you will have a Boltzmann suppression because it's just a Fermi-Dirac or Bose-Einstein distribution. So you have this Boltzmann suppression. But apart from that, anything. Yeah. Yes. Well, yeah. So lighter black holes are hotter, so you can have produce heavier particles. Yeah. Why is this interesting? Because additionally, depending on the amount that you have of black holes, they could even dominate the evolution of the universe before decay. Because at the end, black holes behave like matter. So if you have a little population of these black holes initially, they could end up dominating the universe. We'll have a dominated universe before their evaporation. Okay, and this is what is called will be called the primordial black hole dominated universe. And the interplay between our mechanism, let's say leptogenesis, and the existence of these primordial black holes will depend on when this happens. By this, I mean first, let's say that our leptogenesis models occur in this region 1, right? So leptogenesis stops before black holes evaporate. Things like, since black holes are emitting all types of degrees of freedom, they will increase the number of photons, for instance, that you have. And because of that, you will dilute the asymmetry that you produce. Because just remembering, let's say eta b is equal nb over n gamma, right? So if you increase the amount of photons that you're producing, but you don't change this number, which happens after, let's say, when they evaporate, this will dilute this number, right? This will reduce the number that you had initially. Second scenario as well, this can also happen, but maybe your leptogenesis happened during a matter-dominated background, or it can happen simultaneously the production of your baryon asymmetry to the decay. But importantly, if, let's say, all black holes evaporated before, and then you have leptogenesis, leptogenesis doesn't care if black holes existed or not. You just have a universe that is radiation dominated, and everything happens as before. So how does it relate to the mechanism of leptogenesis I was talking before? So here are the same dashed lines I was showing you before, the abundance of right-handed neutrinos, the abundance of the baryon asymmetry, including this washout delta L equal to processes. But in this case, we have another source of right-handed neutrinos, right? It's not the cosmological, but in this case will be primordial black holes emitting right-handed neutrinos via Hawking evaporation. And the thing is, like, between formation of black holes and evaporation, you're producing right-handed neutrinos, which will decay in the same way, a bias over leptons and antileptons, and this lepton asymmetry will be converted to a baryon asymmetry. And here you see the relation, for instance, I should not have changed the colors. This green line now corresponds to the abundance of the right-handed neutrinos that is produced from the black hole evaporation, and this blue line now is the baryon asymmetry that you're producing from the decay of these right-handed neutrinos. So this is sort of fulfilling this condition I was talking to you before. We are producing right-handed neutrinos after the processes that erase the initial asymmetry are frozen out. So we are producing these right-handed neutrinos when these processes are not important for the evolution of the universe. Okay? And finally, this spike here that you see here is because at the end of the lifetime of the black hole, as I was saying, an explosive process, so you produce a lot of particles at the end of the lifetime. Okay, yeah, I had forgotten I had put those, but okay, yeah, it's the same I just was mentioning. So, okay, we just can look at the parameter space that we're interested in. So in first case, let me just look at the right panel. And this is the panel I showed you at the beginning related to the mass of the right-handed neutrinos to the heaviest neutrino mass. And the green line, the gray line, sorry, is the gray region, sorry, is the one that I was talking about. Now, if we have a population of very, very light black holes, call it saying 0.1 gram, 1 gram, or 10 grams, you open up your parameter space, okay? So you can have, now let's say if you have these very light black holes, you can have any parameters here that will produce the existing baryon asymmetry. If you start to make it, let's say, heavier, since we are talking about very heavy particles, these black holes are not hot enough initially, and you're producing only right-handed neutrinos at the end. This is why these regions are shrinking. Yeah. But this is, since this evaporated very early in the universe, yeah, this is assumed that they evaporated very early. Of course, this is, what you're mentioning is like a primordial black holes evaporating today. Yeah. And then we can just translate, picking some number here, right? Something for the mass and this mass. What are the parameter space that we're interested in? And we see here that there is some, let's say, correlation between the amount of black holes that you need with the masses of black hole, the initial mass of the black holes. But of course, yeah, sorry, again, I forgot I had put this thing. But again, the question would be, can we have primordial black holes this light? We are talking about gram scale black holes, okay? And this is something that we're considering with people at IFT now, if it's possible to really have these light black holes. Additionally, there are other processes, but I think I'm running out of time, so we'll move fast. So since Hawking evaporation is very, let's say, hard, it will create some hotspots around the black holes, right? And let's say there is a non-trivial time dependence of the black holes around there is a non-trivial temperature dependence around the black hole. The mechanism, I will just move on. If you are interested, you can ask me. But the idea is like the temperature profile around the black hole is not what you would expect, but then you create some core that is at some higher temperature than the plasma temperature of the universe. Let's say the average temperature of your universe. So you have a non-trivial dependence as function of the distance from the black hole of the temperature. Why is this interesting? Because let's say even if your universe is cold, maybe inside this what's called hotspot, there is a region in which, for instance, Sphaleron processes may be active. And if you produce some asymmetry, which is, I think, what I'm going to show here, if you produce the asymmetry inside the hotspot, you can convert the asymmetry that you're producing to a baryon asymmetry. So you don't need the universe to be above the electroweak scale. Maybe the universe is only above the electroweak scale in this cold, in this hot region here near the black hole. Okay. We explored this already a year ago, and we were more interested in like the low scale leptogenesis scenario I was discussing before, because we wanted to consider if it's possible to have leptogenesis, including these primordial black holes, in regions that could be tested in future colliders here. So the different stars here are related to different parameters here. And what we find is that, yes, in principle, you need some abundance of black holes. And these don't need to be, let's say, too light. And in this case, still, because of the existence of this hotspot, you can produce enough baryon asymmetry here. Okay. Finally, well, you may be asking, yeah, I'm talking about these primordial black holes in the very early universe. Is it possible to constrain this? And people have computed, for instance, the production of gravitational waves due to the existence of these black holes and the sudden transition between a matter to a radiation dominated universe in this paper here. And they have found that, in principle, you would produce some stochastic gravitational wave background. And as you can see here, these are very light black holes, 100-gram black holes that can be produced, and maybe they can be tested in the future. So in principle, this scenario of having these light black holes could be tested. Also, in principle, the black holes are producing directly gravitons or very, let's say, energetic gravitational waves. But it's much more difficult because, as you can hear, the frequencies we're talking about is 10 to the 16 hertz. So this is way, way, way futuristic in order to look for these gravitational waves. But in principle, they could be there if you had a big enough population of primordial black holes evaporating. Okay, so going back to this, I would just like to conclude a take-home message that, in principle, yes, gravity can play a role in the production of baryon asymmetry, and it could be related to either the high-scale leptogenesis or low-scale leptogenesis. In principle, we talk about two different scenarios: a cosmological production, which comes from this change between inflation, the universe deaccelerating, then reheating, and then a radiation-dominated universe. Because of this, there is an unavoidable number density that is produced. And if one of the particles that is produced are right-handed neutrinos, maybe these right-handed neutrinos could produce the observed baryon asymmetry, even if you have low reheating temperatures. And there is a non-trivial time dependence regarding that. The second case that we considered was the black hole production, in which right-handed neutrinos are produced via Hawking evaporation. And in principle, directly producing in, let's say, for very light black holes, you can sort of save high-scale leptogenesis. And then for low-scale leptogenesis, the existence of this hotspot, we can also produce the baryon asymmetry. But of course, we may need to ask if you can really produce these very light black holes in the early universe, and how this would be related to formation mechanism that I was not considering. And that was it. Thank you very much.
Questions? Yes.
So, if you consider the quantum memory burden for the primordial black hole, what will change? I think it will be lighter primordial black hole.
I'm still being recorded, right? Okay, so I will be very diplomatic in what I'm going to say. I'm very skeptic of the memory burden. There are many assumptions behind it of the memory burden, I think, that the people have considered. I mean, this is very in early stages, because this is based on an analogy, on a supposed analogy between a soliton in a non-abelian gauge theory to a black hole. A soliton doesn't have a singularity, a black hole does. And it's based on this model in which you assume that the black hole is made of gravitons and is basically a condensate of Bose-Einstein of gravitons. That's why I'm saying the analogy between those two things may not occur, and then you need to take the memory burden with a great result. And this is why I'm skeptical. I mean, there is still a lot of work to be done related to that direction. Okay. So yeah, you can have the memory burden, and all this, what I've talked to you, will change because they will have longer lives. So the black holes, they will have larger lives, right? And they will have longer lifetimes. And I think it's about 10 to the 8, 10 to the 9 gram would be still around, depending on some parameters. So they could be dark matter, right? So all the limits I was showing you will shift. Because if a black hole now that, for instance, for BBN is 10 to the 8 gram, it would be still around today, right?
The only thing that will change is the mass scale that you're talking about. You're saying that, but showing that you were saying for 1 gram.
Okay. Yeah, it's easy. Yeah.
Now the memory burden, the only change would be that you need lighter primordial black hole port in that era that you're saying that they got the primordial black hole domination era. That time would change also.
Yes.
What would change?
Yeah. So those mainly those two things, right? Oh no, I'm going to. Here. So in principle, you see, this depends on when the black holes are evaporating, right? And this primordial black hole domination depends on when they evaporate. So if let's say you have the memory burden, these things will shift to the right. Because, for instance, these black holes will be longer lived. So you probably don't need as much as these black holes to dominate the universe, but you will need less black holes to dominate the universe because they will evaporate later, right? So in principle, these things will change. I'm not sure where is the BBN bound, because at some point, I don't know if it's 10 to the 2 grams would evaporate during BBN. But the BBN bound maybe is not at 10 to the 9 gram, but will occur for lighter black holes. Okay.
How we connect scalar field with neutrinos in the cosmology.
Yeah, sorry, maybe I was unclear. So the scalar, it was an example, right? I think I moved too fast there. So what I'm showing you here for the scalar is just an example to understand the origin of this gravitation production, right? This is a scalar. You have this equation of motion that can be reparametrized via something like this. Like try to put an ansatz, and then you find the equation of motion for this alpha, beta, and phi, right? We can do the same for fermions, right? I was just not trying to go into the details of the equation of motion for fermions, but in principle, you can do the same here. And the thing is, like, you find some sort of similar equations of motion for fermions. So this is why this would be the production of right-handed neutrinos that are fermions, right? You mean? Oh, sorry. Here. So, oh yeah, we are assuming that the in is a Bunch-Davis state. Yeah, like this is a vacuum state during inflation, okay? And then we just let it evolve, yeah. So
This is how CMB perturbations
yeah,
are calculated.
exactly. So this is basically the assumption of that is assuming, I think, alpha equal to 1, beta equal to 0, and phi equal to something, right? That translates to some initial conditions on your equations of motion here. I don't remember. I can show you later, but you can basically relate this Bunch-Davis initial state to the initial conditions for these equations of motion.
Next question is, when black hole evaporates, we don't have control of particles.
Mm-hmm.
How do you control this? Because you connect this with right hand.
Yes. Well, the thing is, as I was mentioning before, right? You're producing everything. So when I'm showing this, when I'm showing this, I'm also showing that the black holes are evaporating and everything else, meaning all the standard model degrees of freedom, right? And this is what I was saying, that they will produce, for instance, photons or radiation. This is already included. Maybe I have the questions because I didn't show any question. Let me just. Yeah, here, maybe this simplifies, yeah. So we basically separate, we have these Friedman-Boltzmann equations, right? We have a Boltzmann equation for the evolution of the black hole number densities here, the rho of BH, that is related to the evaporation of the black hole. Then we have, let's say, a branching ratio of the Hawking evaporation into a standard model. And this is what will change the radiation energy density here in this equation, okay? And besides that, we have another equation that is producing the right-handed neutrinos. So we are sort of parameterizing what you're saying, the production of right-handed neutrinos, so a standard model via this parameter here, what we are calling a branching ratio. Let's say the amount of particles that the black hole is producing that are not standard model or are a standard model, right? So, and this is related to the evaporation function I was talking before, this epsilon, right? So this is, in principle, you can separate these two things, yeah. And you solve this system of equations. Once you fix your particle physics model, you do, right? Because, yeah, so this is, sorry, here.
You don't have coupling constants.
Yeah, it's just gravity, right? So basically, you compute this epsilon here. So you're counting all the degrees of freedom, basically each, let's say, quantum particle, and then the spectrum from Hawking, right? So here you can separate all the standard model degrees of freedom, and then you will have another quantity similar for only the right-handed neutrons, right? But there is no coupling. There is, well, that's the coupling is the energy. This is gravity, right? Well, yeah, that's what I was saying. You need to assume a particle physics model. Our particle physics model was standard model plus right-handed neutrons.
But this is gravity.
Yeah, yeah.
Literally the turbulence principle, all particles are created.
But if you're saying that you're assuming a model, then you have a particle content.
Yes.
Then you say that all the particles in this model are created.
Yes, exactly.
But is there a principle for which you have the production of all of them?
No, but this is gravity, right? So it's producing all that exists, right? Yeah.
Everything
Yeah.
is the same.
Yes. So everything that exists. So once you assume that these particles are produced, all of them will be produced from evaporation, right? It depends on the sets of particles, because you can start assuming that there are larger degrees of freedom, or say disconnected sectors or something like that. But once you fix that, everything will be produced.
Really naive out of view question, really broad too. So you have these two models, the cosmological production and the black hole production of matter. So are these two sufficient to explain the current state of matter, antimatter ratio in the universe? Do you need something else?
Yeah, so in principle, yes. For instance, for the, sorry, I was probably not clear. These lines that I was showing you here are the parameters you need in order to produce the observed baryon asymmetry. So each line, of course, it depends on let's say, parameter kappa here, because it's how you parameterize your inflaton potential. But each line will produce the baryon asymmetry here. Yeah, sorry. The same in the case of the black hole. Yes, faster to do this. So here, for instance, this dashed line here, this dashed black line here, will give you the observed baryon asymmetry. So you have more freedom because you can have like enhancements, and then, but in principle there is a parameter. There are some parameters that can produce the observed.